So today's topic doesn't really have much to do with web development directly, but may actually come quite useful. We're going to be talking about neural networks and machine learning in general. So if you don't know what machine learning is, it's basically a set of algorithms that allow us to program and teach our system by example rather than by specifying the rules. This comes useful in a lot of places because usually it's really hard to define the rules properly. For example, imagine that you're building a system that should filter out spam comments. So there's a lot of factors that go in there. For example, how many comments has the same IP been posting for the last hour, or like how many links does the comment have, or is the user posting new or not. There's a lot of stuff going into this, and you want to always be able to update the system and tweak it a bit. So you can't really set hard rules. You can say like, all right, 5 comments per hour, but that's really rigid and it doesn't really take a lot of things into account. I mean, I'd rather have 5 comments that don't have links rather than 3 comments that have like 20 links each. So instead of coming up with rules and combinations, you can build the system really easily that you will spend some time showing, like, say, right, this message is spam, this message is nice, this message is spam. And then it's going to learn from this automatically and be able to classify these messages itself. And it doesn't really stop on classification. You can use it for approximation. So what I have here is a bunch of dots. And let's say you just measured some I don't know, temperature, the change of temperature with regards of pressure or something like that. So basically there's like some correlation between y and x, and you want to plot the rest of this function here. So let's say I have just these points, and I want to know what the value is going to be somewhere about here at this x. So what I could do, I could just take a pencil and draw a line nicely connecting the dots like with some nice logical curves, and then I would say that it's pretty much something like that. And it's easy if you have just a bit of lines, but it gets really hard if you have a lot of those, and then you would somehow have to teach the computer to recognize your handwriting, and so this is not really an option. So instead we can teach the computer to build what he thinks is the best function that represents these dots. So the whole process, and that boils down not only to neural networks but to every machine learning process pretty much out there, is you start with pretty much a random function. Like, let's say this is the green line that we start with. So we just have some random function that doesn't really work for the data. And then over time, with multiple iterations, we try to make it better and make it go through these dots. So like after a bunch of iterations, we can squeeze this green line into this next iteration here, and you can already see that it kind of goes through at least like 3, maybe 4 dots. And then with more and more iterations, just by feeding dots into the system, you get something more accurate like this, and maybe with more time you get like a perfect thing you were looking for. And the best part of this is if you can feed more lines as you go. So if we go back to the spam example, after, let's say I had like this a bunch of rules that were working really good for some time, and then a year passes and the spammers become more savvy and they come up with a different way. So maybe, like, let's say that instead of posting like 5 messages per hour, they are now clever and are posting only 4. And what you can do then is you will feed it more spam messages and say, hey system, you did an error here, so please consider those spam too, and it's going to adjust this curve and filter better the next time. So it's basically like you're giving the system homework and tell it if it's good or not, and if not, it tries to be better, and then you iterate it. So you would say this is a lot of math and processing. It's probably not a very good idea to do it in PHP, and you would be wrong, because I'll show you later. But the spoiler is PHP is actually using C libraries through C bindings, and it is pretty much the same thing as you would be running it from C. So Now let's get into neural networks. And neural networks is a subset of machine learning that tries to approximate these functions using neurons. And the neurons sound very fancy. I'm just going to flip the slide here. So neurons sound very fancy, but in fact, each neuron is a very, very simple thing. And the whole complexity comes from connecting them. So let's try here. This is a simple example, and it would actually work quite well for these for these dots we have here. So let's say we have an X. This is what usually is called the input layer. You can have multiple inputs, obviously, but the important part that wait, I'm gonna get to it. So then there is the hidden layer. The hidden layer is where you have some of your neurons. There can be multiple hidden layers. There can be like one row and the second row, but in a lot of cases, one hidden row is enough. And it's called hidden because it's between input and output. And then there is the output neuron. And the output neuron is the same as the hidden ones. It's just in a different place. Basically, the important part is here. So you have your input, which is the X. And it's connected to every neuron. And if you would have multiple inputs like X1 and X2, those would be also connected to every neuron on the hidden layer. And then every neuron on the hidden layer is connected to every neuron in the output layer, in our case 1, and the output layer outputs the output. And this is what they actually do. Let's go to the next slide, and then we're going to back quickly here. So this looks like math, but it's super simple. Just take a look. So this is a single neuron. So it takes an arbitrary amount of inputs, and to each input it assigns a weight, which is A1, A2, A3. And then it sums all the weights. It multiplies the weight per times input and sums it all up. So you would have sum equals A1 times X1 plus A2 times X2, and I'll do this with all the inputs, sum it together, and pass it to an activation function, which is just a function you don't really need to care about, and then output the result. That's all a neuron does. So in this case, what would happen here would be neuron 1 would multiply X by A1, and then apply the function and return the result. And the result would go here on this line. If you can see my mouse. And then the neuron 2 would do the same thing, and the neuron 3 would do the same thing, and they would feed their outputs to 4, and then 4 would do the exact same thing, and that would produce the result. So the whole trick here is coming up with the numbers A1, A2, A3, A14, A24, A34. So pretty much what the neural network algorithm states, that given a proper set of neurons, and if you guess these weights correctly, you can pretty much approximate a lot of stuff to a very precise point. So the only tricky part is finding A1, A2, A3, and these coefficients. So how does this happen? Well, you start with a random, pretty much you select them randomly at first. There are specific rules that give better results, but it's random. So then you just feed a single dot to it. So I would, let's say this dot has coordinates like 1 and 2. So I would feed 1 here. It would process it and spit out the result. And the result would be something really far from what we were looking for. It would be like 18. And then I would tell the system, no, 18 is not what I was looking for. I want 2. And then there is a special function that goes back here, and that is actually where the math comes in, is the function that goes back. It takes the error that you tell it. I would say, all right, you missed it by 7. So it takes this the error, and it goes back and adjusts all these weights so that the input is going to be closer to, or the output is going to be closer to 7 for this particular input. And then you feed the second dot to it, and then the third one. And pretty much it's going to, so like after you feed it the first dot, it's going to turn this random function that we had here, it's going to turn it into something that goes near the first dot. And then after you feed it the second dot, it's going to make something that goes through the second dot. So the more dots you feed, the more accurate it's going to become. And then you can have and you can feed the dots multiple times. There's like multiple ways with what you can do, but basically the more data you feed the system, the more accurate results you get. So now, even if this looks complex, you don't have to worry, because it's all abstracted, and you're not even going to have to worry about like any math behind it. But the important part to take away from this image is that each neuron does a very, very simple thing. It just multiplies the input by a number and applies a function and returns it. It's like that. So like it's a class with 2 lines of code in it, pretty much. So now let's talk about this activation function that you don't really need to care about, but just so we can dive deeper into this. So you want a function that can do all these nice curves. So you don't want something linear, because if I choose the activation function to be like 2 times x, then I won't be able to have these nice curves, because it's going to just be something linear. So you want a really nice curvy function, and you also want it to be something that has like an upper and a lower bound, so it doesn't go too far. Because if it shoots up into space, then it's not really going to work for you. So you'll have this. Something like this. This is a sigmoid function. There's a lot of functions that look sigmoid, but basically you can see here that it goes like from 0 to 1, or it could go from -1 to 1. You pretty much select the range yourself, and it doesn't go beyond this line up and this down, so it can't get lower than 0. So even if you feed it very, very, very low, like plus 1 million input, it's gonna still be a 1. So the whole difference is going to be happening here. Now, this actually makes things a bit harder, because if you are going to use it, you have to make sure that all your outputs are going to be between 1 and 0, because a neuron simply cannot output anything else, or between 1 and -1. So to do it, you have to do like some normalization. But what you can do for classification, like for example with spam that I told you about, is you can apply a different function, like this one. And it's super simple. You see, basically, if the input is less than 0, it outputs 0. And if the input is larger than 0, it outputs 1. So not the input, but the sum. If the sum, after it multiplied a1 by x1 and added it all together, then it's going to, we'll say 1, and then it's going to say 0. So since this is a linear function, you are pretty much going to get a line like this in the end. And then you can say that everything about this line is not spam, and everything below this line is spam. And every time you feed a new dot to the system, it's going to adjust this line to divide the inputs like somewhere in the middle. And that is called a perceptron. So a perceptron is a binary classifier. It's one of the more useful things that you can do with neural networks. You can there's a lot of things you can classify. For example, you can feed a neural network a picture and say, is this a cat? And after you feed it enough cats, and if you designed the system correctly, it's going to be guessing whether you are showing it another cat or not. So let's take a look here. And one more thing. So I just don't want to confuse you that in case of these neurons, each of them has only one. This one has only one input. So the formula for this neuron 1 would be just x times a1, and that will be the entire sum. And the sum for the fourth neuron will be the output of the first neuron times a14, the output of the second neuron times a24, and the output of the third neuron times a34, and then sum it together and pass it to the sigmoid function. And the sigmoid function that you have in PHP already is 10 hyperbolic tangents. Does PHP have this, like 10h? It should be there. So now let's try and look into some examples. So pretty much it's the library that you're looking for is PHP FANN. It is the fast artificial neural network, right? So they have one example here that you're going to try and look at. XOR training. So XOR training is let's assume we just want to teach the neural network to do the XOR. So it should be able to add, if you so false and false is false, false and true is true, true and false is false, and true and true is false. All right. Basically, if there is one, it's an exclusive OR. Everybody knows that. Sorry. So all you do here is we're going to take a look at this data file later on. But look here. First, they just assign a bunch of variables. It says how many inputs do we have. So since we're training for the XOR function, we have two inputs because that's what we're talking about. So we have two inputs and one output. And the number of layers and the number of neurons on the hidden layer, these things are usually pretty much you have to just decide on, try it, and then if it doesn't work, try another, because due to the whole randomish nature of the process, there are some numbers of neurons and numbers of layers that work better than the other, and it's pretty much very hard to know in advance what's going to be the best for you. But they selected 3 and 3, so it's probably the best thing. Then there is a desired error and max epochs. So what it's going to do is it's going to continue the learning process until the error that it gets is super small, or until it reaches the maximum amount of epochs, which is 500,000 iterations. So this is just the initializing. You pass all the parameters here, and these two functions. It set activation function for the hidden layer and set activation function to the output layer. So they're doing the default one. So the sigmoid function and the sigmoid symmetric function. They're just setting it here. Here we specify the file name for the data, and then we just say it go and train on file until you're done. And then we just we save, and then after it's saved, after it's trained, we save the coefficients to a file so that we can always load it from the file and just fire it up and get the result. And then we destroy it to free it from memory. So pretty much this code here, apart from the number of inputs and outputs, can just stay the same entirely. You can come up with anything. So if I were to train this network for or AND or any other binary operation, I would not need to change anything here. All I would have to do is provide a new data file. So let's take a look at the data file. And it's quite confusing at first, and I found that explanation later on, but really hard to guess what's going on here. So the first row contains 3 numbers. The first number is the amount of test cases that we have, and if you're doing XOR, you have only 4 test cases. You can because you have 2 inputs, and your inputs can only be true and false. So your inputs are going to be false, 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 true, true, false, true, true. So you have 4 sets of inputs. Then there is the number, the amount of input data, which is 2, and the amount of outputs, which is 1. That's why there is 4 to 1. And then each 2 rows of this file represent a data set. So the first row contains the inputs, and the second row the outputs. So pretty much what they mean here is they assigned -1 to, they think of -1 as false, and they think of 1 as true. So what they did is say if it's -1 and -1, then the result is -1. If it's -1 and 1, the result is 1. If it's 1 and -1, the result is 1. And if both are true, the result is false. So this is a small file, and then you run it, and you get the coefficients in this sort of float net. So I did this. It works, but it kind of took a while, and I don't have the extension compiled on this particular computer. That's why I'm explaining it in file instead of just running it. But it just works. It just spits out the result in the end, so it's not really much to see there. So after you have trained the network, and you can have to do it only once, what you can do is test it. So look here. This is they just checking if the file exists. Here they create the network from file, and then they just feed it an input. So an input is an array of -1, 1, which is false true. Then they run the network on the input and get the result, and that is it. So if you would actually run it, you would get the result -1, actually 1, which is true, and you'd be done. So what is the cool part in this? Firstly is when you get new data, you can load the network from file, feed it more data, adjust it, trade it, save it, and continue. So the other cool thing is that this FANN library is actually a C library and has a lot of C binaries in different languages. So you can easily take the same neural network file that it generates with the coefficients and put it in Python, put it in C, put it in C++, and vice versa. So if you find some data that is from you can generate data from Python and then use it in PHP. So one more thing. This is about the classification I was talking about. So how do you actually make it decide whether there is a cat in the picture or not? Because just think of all the inputs. What you would have to feed to it is pretty much every pixel on the image and its value, and that is a huge amount of inputs and would probably take ages to calculate. So, and the system would have a crazy amount of coefficients, which would in turn result in you'd have to feed it a really large amount of cat pictures until it's trained. So instead, what you do is you try to split it in parts, just like their brains work, sort of. You would say, you would first create a mini neural network that would decide whether there's it would try to find if the image is circular. Are there a lot of circles? Are there a lot of parallel lines on it? So you would try to get the features out, and then you would feed the features, like the amount of circles, the amount of lines, the amount of fairy thing on the image. You would feed that to the final network that would tell you if these properties have the are characteristic to a cat. And then you could also reuse it because dogs are also fluffy. You can adjust the thing a bit and feed it to a different network and tell you whether there was a dog on the image. So, wait. Well, since I'm talking about neural networks, I might as well say a few words about genetic algorithms in machine learning. So a genetic algorithm is actually a bit harder, but the thing is, both of them sound really fancy, like the neural networks, the genetic algorithm, and you think they would require a lot of biological stuff, but they are just names, sort of thing. So the genetic algorithm kind of works sort of like evolution. So you would have two random functions, like this one and this one, and you would have a lot of those. You would just randomly generate them, and then you would compare them. But pretty much you would just try and say, does this function satisfy these dots better than this one? And if it does, you would just filter out all the functions that your random generator made that are really bad and keep the really good ones. And what you would do then is take a bunch of really good ones. If you want to be really biological, you would take 2, and then try and average their coefficients together or make some other adjustments. So basically you would come up with like a child, which would be a third function that would inherit some coefficients from one parent, some from the other, some would be averaged, and then you would also add it to the pool, and that would be your first iteration. And then you would do the same thing again. So you kind of mix and then try again, and the general consensus is that after you do this a huge amount of times, the resulting function that you get is going to be way better than the one that you started with, and you can continue running the algorithm and adjusting it until you get all the dots satisfied, or until your the error is enough for you. And then, again, the great part of this is you really have to do very little thinking, and it's really easy to parallel process this, because you can just buy a bunch of computers, feed them a bunch of data. Each computer is going to be processing its own set of children, and there is really not much state in between. Each function is kind of independent of the other, and you can just run it on a huge Amazon cluster, get the results, and then feed the results to your average computer, and you're just gonna give it input, it's gonna apply the function and give you the output greatly. That's why it's way cheaper than hiring actual mathematicians to think of an analytical way of what is spam. So I hope this was interesting to you. If you like more stuff, I can record more stuff on math, because I start to really hate recording stuff about the good practices of programming and things that everybody is doing anyway and don't really bring much new to the table. So, bye-bye.